Welcome to the Network Engineering Video Blog. I'm your host, Michael Crane. Well, today we're not going to talk about lag testing. What we're going to talk about is something that I ran into when I was doing some preliminary testing for this video, actually. And what I had done is I set up the test. This is the way the Xena is set up. You've seen this before. Basically, we have the Xena and 4 ports 0, 1, 2, and 3. The first 3 are tied into the Ethernet switch. The last one is tied into the 3845, and we're going to create 6 streams, send them across our lag and to the gig port on the other side, and then have duplex traffic coming back. And that's all good. And back in, I believe it was blog 28, when we were testing with the MX2s, I had noticed that when I started streams from the Ethernet switch side, I'd start a stream here and start a stream here going northbound. And what was happening is it wasn't load balancing like we had set it in the config. So I thought I would look at that real quick before shooting the video, just to see if it was our test setup that I had before or if it was an actual problem. And so I went ahead and started some traffic on port 0 right here going northbound, and the phone rang, or I got distracted with something, and I walked away and came back 30 minutes later and noticed that not only was I receiving traffic on port 3 from my stream, but I was also receiving traffic on port 1 and 2 as well. And so I wanted to investigate that and show you basically what I had found and how this can be a real trap if you're not careful. Okay, so we're going to go ahead and start some traffic, and this traffic is going to be originating from port 0, stream 0, and it's going to be terminating on port 3, just port 3. And so, and we're just going to be running about 10 meg, and it's just a standard UDP packet, which is a connection list. It's the same. I could have used RTP as well, but we're just going to stick with standard UDP. I'm not going to go too much into the setup of this. It's just the standard stream. It's just Ethernet, no VLAN tags, just a straight IPv4 packet and UDP, and I think we're going to be hitting port 8888. Source and destination. There's the IP addresses, 10.16 to 10.162, and we're going to go ahead and ARP the destination. I'd send an ARP out. He's received the destination address. Oh, here we go, and it actually changed it for me. It's very nice of him. So so this right here is the default gateway. So the Cisco router actually responded to the ARP saying, well, this 162 address, this address right here is not on the local Ethernet switch, so he's got to route it out. And so this is our default gateway from here. Okay, so and you can see how to set all this stuff up in other videos. I want to keep this video short, so I'm not going to go through it again. So we're going to go ahead and start some traffic. Let's see, state enabled. Okay, and start. All right, let's go over some stats over here. See what we got going. Let me clear them out. Okay. So what do we got here? We've got this is some aggregate stream stats. We don't really care about that too much. Errors we can look at. Okay, so the stream traffic stats. So we're going from port 000 to port 003, and we're running about 10 meg. Okay, about 822 to 823 packets per second. And life is good. Not getting any errors, no drops. Okay, so we're just going to let this sit here and run for a bit and see what happens. Okay, so did you see what happened? All of a sudden we went from sending traffic from port 000 to port 003 to sending it from port 000 to all three ports. And it's kind of a strange thing with this Xena gigabit test set. It the way the stats are reading, it sounds like it's port 000 is sending 10 meg to each individual port. And we can go on to switch over here and show that's not really the case. So if we go to show switch int, show int sum, you can see that port 101, which is the one we are sending traffic on, the switch is receiving only 10 meg from it, and it's sending it to on this the second port, the third port, this port down here, which is the lag port. So and just ignore this. This is just management traffic. But yeah, so if I clear these counters, you can see that it really is seeing all this traffic. What's happening is the way Ethernet switches work is they have a MAC address forwarding table. And in Cisco, it's show MAC address. Okay, and you can see these are the dynamic ones that it learns. And you can see that this is our source port, right? He knows the MAC address of it and the physical port he's hanging off of. And these are our lag ports right here, okay? But he doesn't have the default gateway MAC address. And that's a problem for Ethernet. If he doesn't know where to go, if the switch doesn't know where to send a Ethernet frame when it receives it, he decides just to send it everywhere. And some people call it broadcasting. Some people call it unicast flooding. Whatever you want to call it. It basically turns into an Ethernet hub at this point. It's just sending. It can't find anything, so it just sends it everywhere, and it literally hopes it sticks. So if you look at our table now, if you look at the test equipment now, you can see on ports 1 and 2 on the test and the Xena gigabit test set that we're no longer receiving traffic on that any longer. So if we go back over here to our MAC table and repeat that command, you can see on port 1 right here that it now has the MAC address for our default gateway, which is what is in our it's what we ARPed earlier, if you remember. We'll go back over and look at it real quick. Yeah, so 0360 is our default gateway. Remember when I sent the ARP, that sucked in and changed our default gateway. Well, now you can see it's in here, 0360. So, and that's why the traffic is not getting broadcast. Oh, now you can see it just came back. So what's happening is the MAC table isn't getting updated fast enough to keep that MAC from aging out and broadcasting, and thus causing broadcast or to flood the entire switch with our 10 meg of traffic. And you can imagine all 40 of these ports, or 48 of these ports provisioned, it would be sending 10 megs of traffic on each one of them. And you get a couple streams like that going, and you'll fill up an Ethernet switch lightning fast. I also wanted to mention that there are other causes to what Cisco calls unicast flooding. Some people call it broadcasting packets. In the olden days, the hub repeaters, they just called repeating on all ports. But anyway, whatever you want to call it, it's a normal function of an Ethernet switch to do this. So, but there are other causes for it, and I found a document that that Cisco had for the very, very old 6900 or 6509, I mean, and they talk about the different problems that cause it. So they have the asymmetric routing, which is basically what we're doing right now, and then they have the spanning tree protocol topology changes, and then we have a forwarding table overflow. And the way you check those things, just quickly, show spanning tree, VLAN 10, detail. You can see that topology change, oops, wrong one. The number of topology changes has 7, and the last change occurred 5 days ago. So, believe me, it is not spanning tree that's causing the problem. So, so we know it's not a spanning tree topology change. Another one is a forwarding table overflow, and the way you check that is you do a show MAC address table, and then count. And as you can see, we have 5,508 MAC address spaces available. Yeah, see, we're only using 5 dynamic ones, so we know it's not that. So it's this asymmetric routing, and you can read this. I can link this in the comments if you want. But this is kind of a unique situation that they're referring to. The more common situation is when you have VoIP. And I'll show you, and I'll talk about that here in a minute. So how do we detect when our switch is broadcasting traffic to all ports or unicast flooding? Well, that's kind of a problem, because since it's a normal function of an Ethernet switch to do this, most switches don't see it as a problem. However, it can be a problem if it's flooding your network. So to detect what's going on, we can look at the Cisco document, and it has something, but it's so old. It's 12.1. It's for the 6500 series, that this command isn't even there anymore. Which actually, I'm surprised it's still not in there, because that would have been kind of handy. You could have probably made something to parse a log file every now and then and raised an alarm if you had something going crazy. But the only other thing they really give you nowadays is to use storm control to to detect it. So, and storm control actually will stop it. And I'm not going to go into storm control. I'd have to do some research on setting it up. Or if other people have other ideas of detecting this unicast flooding, it would be interesting to post them in the comments and share it with people, because I have poked around before trying to detect this, and I haven't found a solution that I really liked. Okay, so how do we fix this? We know we can't really detect it very well, so maybe we should just jump straight to the fix. There are a couple options that we have. One of them is to set the Mac forwarding table timeout just a longer period. So if we do a show Mac address table aging, you can see the global aging time is 300, and I'm sure it's the same for the VLAN. So if we do show aging VLAN 10, it's also 300. So it's just using whatever we had in there. And so if you have a VLAN that's set up just for voice traffic or RTP or maybe some kind of UDP traffic like file transfers or something that is going to have this problem, you could set it. Or you could just, set the global time. So you could just do a config T. Let's see, it's a Mac address table aging time, and you can either disable the aging, which I think is a very bad idea, or you can set the aging time, and as you can see, you can set it pretty long. That'd be 1, 2, 3. What's that? 1,000,000 seconds or something like that. Don't know how long that is, but it's a pretty long time. So that's one way of doing it. I'm not thrilled with either one of those. The default is about 5 minutes, and if you have a busy network, you probably don't want your Mac table forwarding to overflow. We only have 5,500 entries, and like I said, if you have a busy network, it could become a problem. Okay, so what's the other one if we're not going to do that? Well, you can block unicast traffic. You can say, okay, I don't want that, and that can be done. I'm not going to go into the commands. You can do that with storm control or some other settings to just block the unicast traffic. If you Google block unicast traffic for your router, I'm sure you'll find the commands for it. But my favorite one is I want to send ARPs. We know that if we send an ARP, it will update that MAC table in our Ethernet switch. And the MAC forwarding, I should say, in our Ethernet switch, and that's kind of a nice fix. And actually, if you dig around through one of the specs, I forget which one it actually is. If you Google forwarding, layer 2 forwarding, or maybe it's ARP update on the host, you'll see that it's recommended to not send over more than one every second. If we come over to our port and send an ARP out, it will populate our MAC forwarding table. Okay. For every 5 minutes. And I kind of like that. So with our test equipment here, it doesn't really do that automatically. So we're going to have to come up with some kind of, I don't want to call it a workaround, but some kind of way of keeping our Ethernet switch alive with our unicast traffic. But if you're using some kind of phone, IP phone, or some other host that uses unicast, or it's a voice type system, usually it'll have some kind of keep alive. The only time you're going to really have this problem is if you have, let's say you have a machine that's calling somebody, and it's only a one-way audio. Say like you're announcing something and it's going to last a while, or maybe you're playing a message for somebody, and it's very long. Then you can have problems. If it's two-way audio and it's both on the same path, then the Ethernet switch won't need these keep alives. But we happen to need it for our test equipment. We're receiving traffic on the other two ports. If we look at our MAC table, show MAC address table, you can see that our default gateway 0360, you can see that it's not in our table anymore. If we send an ARP, okay, and go look, (0360) is right there. So we know the ARP is going to work. And since this is a test box, it doesn't really have a send keep alive ARPs. We're network engineers. We don't need it, right? Okay, so we're going to fix this by adding our own ARP, keep alive. So we're going to add a new stream, okay? And we want it to be, we're just going to call it our ARP stream. And we want it enabled. We're going to set it real low. We want it 1 packet per second. Okay, that's about as low as we can get. And we want it 64 bytes in size. I think we're going to have to make this bigger because of the test set. And we want it pattern just all zeros. Okay. We don't want any test payload or any of that other stuff. And okay, so we're going to come down here, and this is going to be a broadcast ARP. And so our destination MAC, we don't know it. So we're just going to say FF in the destination MAC, okay? Then we're going to add another segment here. We're going to say it's an ARP. Okay. And now it's complaining that we need to make the stream bigger. Okay, so we're going to make it, it said 66, I'm going to set it to 68. Okay. And we're going to go down here and protocol length. Okay, everything's good. So our sender hardware address is going to be this guy right here. So the 61E0. So we're going to say 04 F4 BC 10 61E0. Alright, and our IP address is going to be 192.168.10.16 for this port. Our target address, we don't know, so we're just going to leave it all zeros, right? And our target IP address is going to be 192.168.10.162, because that's where we're wanting to go. Okay. Let's go back up here and start our traffic. All right. And go with our global stats. I'm going to clear them. And oh, okay. So so you can see, we do have ports 1 and 2 showing stats, but you can see our packets per second are 1 per second. And what that means is our broadcast ARP is getting broadcast to those ports. All right. Which means they should be getting broadcast to the router ports. And what we'll find is now that we've got that stream going, we shouldn't have any more problems with the switch MAC at the MAC timing out. So you can see it right there. And it doesn't really show any aging, which is too bad. That would have been nice to see. Okay, so let's clear our counters. So we'll do a clear count. Yep. And show interface summary. All right, as you can see, we're receiving about 10 meg on our first port, which is right. And we're only sending it out on our first lag port, which is good. So we're going to let this run for a bit. I'll pause the video. We'll come back after a while, and we'll see that without ever going into broadcast mode or unicast flooding mode. Okay, so you can see I let it run overnight. And as you can see, it seems to be we didn't have any problems. We've got some traffic on these ARP streams, but if we were getting more broadcast traffic, it would we would see 2 more streams on here. So I am happy with that. That looks like it's going to work for us. And with the stats, when we go to set up the stats, I should be able to filter this traffic out so it doesn't affect our other traffic. Yeah, it's going to take a little bit of the bandwidth away, but it's going to be just dinky because these are just little 64-byte packets going at 1 per second, and yeah, that's going to be a drop in the proverbial bucket. As you can see, the ARP fixed our problem, and that's good. And you might be asking yourself, why would you have this type of unicast traffic? And I'll give you an example of where I actually ran into it in the field. And I'm going to draw it up in the corner here because this is for another video. So if you have a switch, let's say it's a soft switch, telephone switch, and it's got a controller up here, and then it's got a media gateway down here, and it's using some kind of signaling. What you're going to find a lot of times is what they'll do is the controller will be in one network, let's say VLAN, I don't know, 10, and all the RTP traffic will be in another network, say VLAN 11. And so if you're getting one-way traffic through these Ethernet switches, what's going to happen if it's not getting any kind of duplex traffic back to it to keep this MAC forwarding table opened up, what's going to happen is you're going to lose that MAC forwarding table is going to lose its forwarding, and then it's going to start broadcasting these audio streams all across the network, and it can be very bad. And I have actually seen this happen. So yeah, don't think it doesn't happen, and that's why the option of blocking unicast I thought was such a bad idea, because you don't know what your customers are putting on there. But it's best just to, if you can, set up some kind of ARP or keep alive mechanism from your media gateway. It can be a ping, it can be an ARP, you know, anything that maybe pings your gateway. Oops. Right here to make sure all this stays alive. That way, I mean, most of your traffic is going to be going through a gateway anyway. You don't want your switches to lose track of your gateway MAC address. So anyway, that's it. I hope you liked this video. If you have any questions or comments, leave them in the comments below, and or your questions, leave them in the comments, and I'll see you later.